Hello everybody, this is Mesa Merhaban. Hope you're having a great day. Here we are for the second demo on battery technologies. This is the second YouTube short. We had one before, which focused mostly on new battery technologies and market research, and there will be one after this. I've been with Oz Engineering for more than a year. Before that, I was with an electric vehicle startup called Python, and before that, I was with Ford Motor Company for almost 5 years. What are we as Oz Engineering? We are an elite channel partner at ANSYS. We have been in the Bay Area for 17 plus years and 1,000 plus happy clients. We sell ANSYS products. We do customer support and also conduct trainings. Sometimes we do projects as well. We sell simulation tools for modeling multi-physics finite element analysis or FEA, computational fluid dynamics or CFD, and also electronics and electromagnetics, which includes high and low frequency. And as I mentioned, we have been the year channel partner of in the whole US for several times. This is the list of softwares that we can sell and we provide. As you see, it's a large number of software. We have tools in structural mechanics, such as mechanical or Elastina or Encode in fluid dynamics, such as Fluent, CFX, and Polyflow, etc. In electronics, we have Maxwell, HFSS, SI-Wave, and also tools for motor design. We have semiconductor tools and also optics. And except for these categories, we even have some other categories, like one is for materials, such as Granta, for embedded software, which is a SCADE, and for systems, which is Twin Builder, and Medini, which is a tool for functional safety. So as you see, as a part of ANSYS family, we are a very big company. We have a lot of tools. So whatever is your field, feel free to ping us. We definitely have a tool that can help you and make your job easier. The outline is that first we wanted to do a market research and go through the new battery technologies. We did that in the first YouTube short. And in this one, we'll go over the reduce order models and also digital twin. We after that would focus on battery management system or BMS and the answer solution for this challenging problem. After that, there will be a system level modeling, so you can see how things works in a big system, and then an example and demo problem, which would be the battery pack with a fan and probably a switch. So the last two probably would be in the third YouTube short. As mentioned before, so we have a lot of money which is being put in the R&D for battery. A lot of new battery technologies are coming in. And for now, we have lithium ion as the leading technology, but it's going to change and it's very dynamic. But what is the Fluent scope for the different battery technology modeling? Fluent can do electrochemistry, direct electrochemistry. Let's say you have the geometry of the battery cell and the materials, and based on that, you can predict how much is the current it can create. This can be done with direct electrochemistry. This is only applicable in lithium-ion battery. And unfortunately, it does not apply to new battery technologies such as solid state or sulfur ion. The other method to take care of the electrochemistry part is the ECM or equivalent circuit model, which definitely applies to lithium ion as well. But definitely it is possible to apply it to new battery technologies because it creates a circuit model, and based on the test data, usually HPPC test data, it fine tunes it so it can predict the behavior of the cell. This approach is highly recommended for electrochemistry because it's quite independent of the type of battery you're using, and you just need some sort of test data for it. The other approach is the thermal. So this takes care of the conjugate heat transfer behavior. As you see in the battery, you have a lot of heat transfer, you have a lot of heat generation, and to see how the heat travels in different parts of the battery pack, you need to have a conjugate heat transfer model. This can be applied to lithium ion batteries definitely, but even for other types of battery, this can be used. As long as you know how much heat you're generating, it doesn't really matter what kind of battery it is. For reduced order models or ROMs and digital twins, we can say the steps as below. We can use Twin Builder to prepare thermal LTI ROMs by Fluent results. And after that, when we have the LTI ROM for the conjugate heat transfer, then we can generate the ECM in Twin Builder, which would be a Modelica model. ECM stands for equivalent circuit model. As I mentioned, for the electrochemical behavior of the battery, they use it to replicate it with a circuit, and those circuit properties are being fine-tuned based on the performance or test data. At the next step, you can couple the ECM model with the thermal ROM, and in case you do that, then you will create a electrothermal coupled model. Sometimes they call it ETC. These are the most three steps you need for creating a ROM or digital twin from a battery. But there is also one other option for ROM that it's kind of optional. You don't apply it in all the cases, but I wanted to touch it so you guys are familiar with it. For potential, when you're using the lithium ion MSMD model, you have two options. You can directly solve for the potential equation, which is a little more expensive, but there is another approach that you can have something like an analytical model. So you can calculate it much faster. That is sometimes called the potential ROM or reduced order model. We'll go through that in a little more details in the next couple of slides. Here you see how to create a thermal ROM in Fluent, as you see. To do that, you need to bring the data from Fluent into Twin Builder. So initially you bring the geometry into Fluent, you create the conjugate heat transfer, and then you feed those data, which is mostly like in the text or Excel format, inside the Twin Builder into a reduced order model. You can have different options. You can have, let's say, single input, multiple output ROMs, which means that you treat the cells that you have in a module as uniform. They say you assume they all have the same temperature, for example. Or you can have MIMO, which stands for multi-input, multi-output, which means that for each cell you calculate how much is the heat loss, how much is the heat rejection, how much is the heat generation and temperature associated with that. So you don't look at them as a bundle. You solve them individually. Here are some examples. As you see, one is the one on the top left is the multi-input, multi-output. As you see, there is input for each cell inside the module. On the top, there's just one, but different outputs, so you assume they're all uniform. And then on the bottom left also, it's some case, sometimes they use the acronym CISO for it, which is single input, single output, which you're just selling not a module, just a single cell. After that, you need to create the ECM or equivalent circuit model inside the Twin Builder. But how do you do that? It's quite straightforward. As I mentioned, you go to Twin Builder and then you go to a toolkit, which is a battery wizard. And after that, you choose the self configuration tool. Based on that, you would be able to bring the data. As you see on the right hand side picture, it's like an equivalent circuit model of a battery. This is the format which has been used for from different literatures, and everybody uses that. You create electrical circuit similar to this, and you populate the properties of, let's say, resistances and capacitances until it matches closely with the experimental data you have. As I mentioned, after bringing the data into the toolkit, you'll have this wizard that opens up, and then you have all these options. You want to have how many parameters inside the ECM model. You want to have what parameters as independent variables, how many cells you have, and then you bring the data. Based on that, you can easily generate a ECM model in Twin Builder. These models are mostly Modelica, as you see on the right hand side. That's an example. When you bring the data, the test data, mostly you have this Modelica model, which represents the electrochemical behavior of the battery. And the next step is to create the ETC model, which is electrothermally coupled model. To do that, all you need to do is that you have the LTI ROM already, which is the left hand side block, and then you have the Modelica, which is the right hand side block, which represents the equivalent circuit model for the battery cell, and then you connect them as the following. The way that it works is that the Modelica model, which is the ECM model, tells you how much is the heat loss in each of the cells, and then you feed that to the LTI ROM, and the thermal ROM, based on the heat loss, can tell you what's the temperature in each of the cells, and then based on the temperature you can again predict the electrochemical behavior of each cell. So you feed it back into the ECM, and both these together, when they're coupled, they pretty much can represent both the thermal and the electrochemical behavior of the cell or the module that you're dealing with. Here's the approach that I described in the last couple of slides. You see, first you have test data, let's say HPPC test data, then you create a cell ECM or a module ECM out of it, and then you transfer it into a Modelica model, which is an ECM model. And for the conjugate heat transfer, you bring the geometry into Fluent, you create a module conjugate heat transfer model, and then you create some data and then use those data inside the Twin Builder to create a thermal ROM. And when you connect these two together to represent the battery module, this is called the ETC, or electrothermally coupled model. You can connect these two together to represent maybe a battery pack in a vehicle, or you can connect it to some heat loss values to represent the cooling, maybe by a cooling plate in a car. Here is a battery pack solution. As you see here, you see how the temperature changes. One of the modules is overheating and one of the cells inside of it is really hot. So this behavior has been captured by this method. And as I mentioned, there's also a ROM for potentials. This is only for lithium ion multi-scale multi-dimensional method. And if you're using MSMD framework, you need to solve for two potentials in the transient solver, as you see. We can make some simplifications for these differential equations under uniform electrochemical reaction conditions, which is a good assumption. We can simplify these equations and obtain the potential fields by solving them directly, almost analytically. So instead of solving these PDEs numerically, we just solve it directly and calculate the values associated with that. This is sometimes mentioned as the reduced order model for potential. So you do that, you just need to check this option in the battery module. As I mentioned, this is just approximation, but it's close enough so you can use it. And usually before using this reduce order method or model, you need to first use the solver solving like transport equations for a couple of steps, so you can get some reference field, and from there you can activate the reduce order model and keep iterating. The other topic that I wanted to touch is the battery management system. First, we go on this topic that what exactly BMS is, what does it do, what are the challenges. After that, we go over the safety critical issues about battery and ISO 26262 compliance. After that, we will focus on ANSYS approach for modeling BMS, which is based on using Medini, Skate, and also Twin Builder. And later that we'll focus on the fact that ANSYS approach is quite cost effective compared to any other approach that is in the market at the moment. What is BMS? Just to summarize, we can see that when you have a car with a lot of batteries in it, you need to control all the cells and make sure they're all in a good operating range. They're not too hot, they're not too cold. The state of charge is reasonable. And you know that software and hardware, they work together to monitor the battery performance and also its usage. This is very complicated. You have a large number of cells, and cells are pretty sensitive. It's hard to keep them in optimal operating conditions. And the challenges that it has is that it's very critical to safety and performance. And it also impacts the weight and also mechanical and thermal subsystems. And it's very expensive to test via iterations. So we need to do it in the virtual world using simulation. Managing BMS design and complexity while reducing development costs and improving performance is quite tough. And the other thing is that because it's a safety critical issue, it needs to have compliance with standards such as ISO 26262, which is not cheap. For BMS design, there are some challenges and also some capabilities which are desirable, but we'll go through it. Some of the challenges is that if we don't have the model-based design and you want to do it the traditional way, you need to do system safety analysis, which has its own issue. It has problems with traceability. As I mentioned, the manual software development is costly. It takes a long time and it's very prone to errors. Validation and verification activities are quite also hard to do. It's hard to have traceability on these kind of activities when you do it manually. And when you go to testing, it would be very late, so you can test the whole, let's say, battery pack. Based on the reasons I mentioned, this is very costly and also it takes a good amount of time. The required capabilities that you want is that you want to have the architecture-driven functional safety analysis tools, so you can do things much faster. And then the other thing that you probably need to have is the model-based design rather than the manual way of writing the control system for battery. For creating the codes, you need to have a method for certified code generation, so the code is already having compliance with ISO 26262, and the system level simulation is also something required, so it can integrate the high fidelity and also complex behavior of the system. and you need to be able to test the BMS response under various conditions like fast charge, different drive cycles, and based on that, you'll be able to calibrate that. ANSYS has its approach for writing the BMS. What it recommends is that you use Medini to do the functional safety analysis. First of all, you need to do a, let's say, fault tree analysis or FEMA or HIRA, which these are methods that tells you the potential for failure in a complicated system. And after that, when you cut those failure modes, you would pass them into ANSYS Cascade. ANSYS Cascade would be able to create qualified model-based code. Instead of writing codes manually, which is prone to a lot of errors, you can create a code based on the model-based design, based on these logos and logics as you see here. And you will be able to check if this has compliance with the standards or no. And after that, you can pass this into the physics-based battery simulation, which is done inside Twin Builder. When you have checked this code, you know it's reliable, it has no issues regarding functional safety, then you implement it inside the ANSYS Twin Builder, so you can predict the behavior of the system based on the BMS control mechanism. The other thing which is worth mentioning is that everybody tries to cut costs, and ANSYS approach for doing BMS is quite cost effective. So you use Medini because it supports all the functional activities. Use Skate because it supports all the software developments for ISO 26262, as I mentioned, and also AutoSAR and also ASPICE. Usually this way it's 40 to 50% cheaper than the traditional way, and the whole product development, as you see during this V cycle, it's almost 2 times faster. So you can get your product out in a shorter amount of time. And actually that means cheaper too, because time is money, and then you can create a high quality code in a shorter time. This was the summary mostly on BMS, and thanks for listening. If you guys had any other questions, please email us and I'll be more than happy to respond to you. Thanks for your time. Have a great day. Bye.